My name is Kim, and we're here to do some important work today as we begin to learn how scientists count, weigh, and measure different chemical substances. Our learning goals for this video are to explain why counting by weighing is important for chemists, to explain how we can count by weighing using an example, to define 1 mole, and to use the periodic table to find the molar mass of an element. For this video, you should have access to your New York State reference table with your periodic table, and you should have a pen or a pencil and something to take notes on and something to take notes with. Let's get to it.
Something you may have had some experience counting before is spare change. So let's count, these are all dimes. Let's count how many we have. We're going to start off doing it the old-fashioned way, just counting by hand. It can take a while. I wonder if there's a better way. For those of you who are counting along with me, that comes out to 37 dimes. Imagine trying to count the number of atoms in a substance like this. I mean, you can't imagine it because it would be impossible. Atoms are too small and there are too many of them. So we're going to look at an example of how I would count this sample of change, this sample of dimes, by weighing them instead of by physically counting each dime.
So if I have a balance or a small scale to measure mass, and I have 1 dime, I can find the mass of 1 dime. So the mass of this dime is 2.27 grams.
We know that 1 dime has a mass of 2.27 grams. And I just want us to quickly think about how we can represent that using units and numbers, right? So there's 2.27 grams for every 1 dime. That's sort of what we're saying in English. We can write that as a fraction, as a ratio. We can say there's 2.27 grams for every, and draw that fraction line to represent for every 1 dime. That's a totally valid way to write that ratio. We could also simplify it even more. And this is where we get into units that have fractions in them. So because we are talking about the ratio of grams to every 1 dime, we can kind of make that 1 in the denominator there kind of invisible and just write the unit. And so what we can write is that there are 2.27 grams per dime using units as a fraction. So when I see, as a scientist, 2.27 grams over dimes, what that reads to me as is for every 2.27 grams, there is 1 dime. And so there's just a quick note on how we use units as fractions, right? We're talking about ratios.
So if we know that the mass of 1 dime is 2.27 grams, assuming all of the dimes in the pile were minted or manufactured the same way, so they all have the same mass as each other, what should we do to figure out how many dimes we have without having to physically count them all? I want you to pause this video right now and think for like 30 seconds about this prompt. What should we do so that we don't have to physically count all of the dimes?
Hopefully, your thought was, let's just put all of the dimes that we have onto the balance and find the mass of my entire pile of dimes all together. Let's go ahead and do that.
Just because my balance is small, I'm going to zero the balance with a little baggie on it so that I'm not getting the mass of the bag, and then I'm going to put all the dimes into the bag so that I can find all of their mass without any of them falling off the balance. So I'm going to go ahead and find the mass of all of this pile of some number of dimes, and 84.30 grams is the mass of all my dimes.
So we have a total of 84.30 grams when we put all of our dimes on the balance. And we know that we have 2.27 grams for every 1 dime. We're going to use this information to see if we can work out how to solve for the number of dimes that we had, counting by weighing and doing a little bit of math instead of physically counting. So I can think about this as, I know that if I take the number of dimes and multiply it by the mass of 1 dime, right? So if there were 2 dimes and I multiply 2 times 2.27, that should give me the mass of 2 dimes. If there were 5 dimes, I should take the mass of 1 dime, 2.27, and multiply it by 5 to give me the mass of 5 dimes. So I know that my equation for figuring out the mass of all of the dimes together should be the number of total dimes times the mass of one dime. I know the mass of one dime, and I know the mass of all the dimes. I measured both of those variables. What I don't know is the number of dimes, and I can solve for that in my equation. So I can say the number of dimes that I have in total should be equal to the mass of all of the dimes divided by the mass of one dime. And that's just from rearranging the equation. So the number of dimes should equal 84.30 grams divided by 2.27 grams per dime. So my number of dimes, when I put that into a calculator, I'm going to get about 37.1 when I round to three significant figures. Now notice this is not a whole number. When we are actually collecting data using real life tools like that balance that I used, we often, particularly when we're doing calculations in stoichiometry, do end up needing to do a little bit of rounding and accepting the fact that our measurement tools are not perfect. This is where percent error calculations get really relevant. But 37.1, that's really close to the number 37. And I know from when I physically counted the dimes before that, yeah, there are 37 dimes there. So 37 is the number of dimes that I have in my collection there. I could have figured that out by just weighing one dime and then weighing all the dimes and then doing a little bit of math, right? I didn't need to sit there and physically count out every single coin if I had a balance. So you might be thinking, that was really impressive, Kim. You counted how many dimes you had without having to actually physically count them. Great. What does this have to do with chemistry? Well, counting by weighing is not just useful for determining amounts of change. If we know the total mass of a given substance, so I figured out the mass of all of the dimes that I had, right, in that example that I just did, and we know the mass of one unit of that substance, we can count how many units of that substance we have. So there's one pretty big problem with just going straight to saying, okay, I can count the number of items by weighing as long as I know the mass of one of those items. There's a problem with that when it comes to atoms. You might have thought of this already, but atoms are very small. Like they're really, really, really small, right? I could physically count the number of coins on the table in front of me. It might be annoying to do so because there might be a lot of them, but I can physically do it. We can't physically count atoms. And what's more than that, they are so small that one individual atom is going to have such a minuscule mass compared to the masses of things that we measure using our everyday tools. So most balances that we use can measure to the hundredth of a gram, but one atom of carbon has a mass of, well, 1 times 10 to the negative 23rd grams. That's a really small number that's not very useful to use in calculations and really, frankly, just not very useful for the human mind to conceptualize. And so instead of counting and weighing individual atoms of individual elements, scientists decided a long time ago to count atoms by groups, right? So rather than finding the mass of one atom, scientists decided to count by one set unit of a big group of atoms. Hearing the word mole may sound strange at first, but we already use other words to describe groups of numbers. For example, the word pair, as in I have a pair of shoes, just means 2 shoes. If you say you have 3 pairs of shoes, it means you have 6 total shoes, right? 3 pairs. A dozen, right, refers to 12. You buy 1 or 2 dozen eggs, you know that you're buying 12 or 24 eggs. You can think about the mole as just another word that represents a quantity. The difference is a mole is a really big number, like really big. 602 hexillion, that's a big number. So 1 mole is equal to, you'll usually see this number, 6.02 times 10 to the 23rd. So when we are counting by weighing and we're talking about atoms and molecules, we don't weigh the mass of one atom or one molecule. We start from the mass of 1 mole of atoms or molecules. This is why the periodic table is just so awesome.
Bear with me here. You'll see that it's true. You know that number in the upper left corner? That number that says atomic mass? Let's look at the key. We can see there's carbon, there's its atomic mass. Turns out that atomic mass is also known as the molar mass. No, not molar like your teeth, molar like 1 mole. That number tells us the mass of 1 mole of atoms of that element. Say it one more time. That upper left-hand number on the periodic table tells us the molar mass, or the mass of 1 mole of atoms of that element. So 602 hexillion carbon atoms weigh 12.011 grams.
One final opportunity here to make this analogy between what we did with the dimes and what's happening on the periodic table as clear as possible. So we knew that the mass of 1 dime was 2.27 grams. This allowed us to figure out how many total dimes we had by finding the mass of a bunch of dimes, comparing it to the mass of 1 dime, and doing some math. So the periodic table, by giving us the molar mass, or the mass of 1 mole, or 602 hexillion, or 6.02 times 10 to the 23rd carbon atoms, it's the same idea. So the periodic table tells me that carbon has a molar mass of 12.011 grams per mole. That means that 1 mole of carbon atoms, just a much simpler, nicer thing to look at, right? 1 mole compared to 6.02 times 10 to the 23rd. I don't know about you, but I prefer thinking about 1 mole. So 1 mole of carbon atoms, I just know that it's that big number, has a mass of 12.011 grams. 602 hexillion carbon atoms have a mass of 12.011 grams. I'm going to count by moles when I think about the molar mass of substances, because it's not useful to think in terms of 602 hexillion. Don't you agree? It's much nicer to just say 1 mole, half a mole, 3 moles. It's a nicer way to use numbers and not have to be using scientific notation. So what I would like you to do is use your periodic table right now and see if you can follow the pattern that I did with carbon and determine the mass of 1 mole of aluminum, hydrogen, and potassium. So pause the video and press play when you're ready to give it a try. All right, hopefully you gave it a try. The periodic table, if you look at table S, it gives the molar mass in the top left of the box. Aluminum is atomic number 13. So the mass of 1 mole of aluminum atoms would be 26.98154 grams. Your teachers or your instructions will tell you if you should round to a certain number of significant figures. But as default, I usually just write down whatever all the digits given to me by the resource were. Hydrogen, the mass of 1 mole of hydrogen atoms, according to your periodic table, is 1.00794 grams. And the mass of 1 mole of potassium atoms would be 39.0983 grams. Again, these are all just numbers that are coming off of our periodic table. So now we know 602 hexillion aluminum atoms has a mass of 26.98154 grams. This is going to be very useful information for us in the future.